Hello, I'm Sylvia Knight, Head of Education at the Royal Meteorological Society. In this series of short films, we are going to be covering some of the background information that teachers may find useful if they are teaching weather and climate at secondary level, and specifically if they are using our weather and climate teaching guide with accompanying classroom resources which can be found on our website, Metlink. In this film, I'll be looking at weather and climate. Climate is what we expect. Weather is what we get. So weather is the day-to-day state of the atmosphere and its short-term variations in minutes to weeks. This includes factors such as temperature, humidity, precipitation, cloudiness, visibility, and wind. Climate is the average weather for a given place. Usually, that's the same as saying that it's the weather we can get most often in a given place and at a given time. Climate information includes statistical weather information that tells us about the normal weather as well as the range of weather extremes for a location. Usually the climate is taken to be the 30-year average of the weather. So for example, this temperature box and whisker graph shows that the July maximum temperature climate for Rochdale is 19.7 degrees Celsius. That's the black line. The green lines show that 60% of the time the temperature is between 21 degrees and 18.2 degrees. 20% of the time it's warmer than 21 degrees and 20% of the time it's colder than 18.2 degrees. So on a given July day in Rochdale, the maximum temperature might be 29 degrees, but if you were asked what you thought the maximum temperature would be on that same day in a year's time, the correct answer should be 19.7 degrees. Why is it so hard to predict the weather a week in advance, and how can scientists tell us what they think the climate will be like in 50 years' time? Well, first of all, it's important to understand that weather isn't random, it's chaotic. That means if the weather were random, it would mean that there would be no possible way of knowing what it was going to do next. However, the weather does obey the laws of physics, and every change in the weather has a cause. The problem is that since there are so many possible causes, we can't know about them all. You may have heard of the butterfly effect, first proposed by Ed Lorenz in the 1960s. A butterfly flapping its wings in the Amazon rainforest might, through a long line of unlikely but possible consequences, cause a storm over Texas. In a similar vein, if we don't know what's going on in the atmosphere and on the Earth's surface down to the detail of a butterfly flapping its wings now, we can't hope to know what will affect the weather in a week's time. The possible range of consequences grows with time, and the ability to accurately forecast the weather will decrease. Of course, some weather situations are much easier to predict than others. For example, high pressure is easier to predict than the snow showers which can be caused by an Arctic maritime air mass. But in general, tomorrow's weather forecast is much more likely to be accurate than one for 10 days' time. In this figure, you can see the growth of the range of possible temperatures in a 5-day weather forecast. Modern forecasting techniques try to capture the range of possible future weather by making an ensemble of weather forecasts. Rather than making one forecast with one set of starting or initial conditions, the weather which is right now, they make many forecasts, each with tiny but plausible differences in what the weather is now at the start of the forecast. Each difference represents the effects of all the possible butterflies or other tiny details about the climate system that we can't possibly measure. The ensemble of forecasts give forecasters a range of possible weather forecasts and provide some indication of what is most likely and what might happen but is less likely. This leads to weather apps now frequently given the probability, for example, of rainfall for a given place. The climate, unlike the weather, is not chaotic. Remembering that climate is average weather, if the large-scale factors which control the climate are known, so for example the composition of the atmosphere, the location of the continents, the Earth's position in relation to the sun and all the other things, then it's possible to predict the climate. Climate is to weather as the bank is to the roulette wheel. The statistics of the system are simpler than the system itself, and so it's easier to be right in the long run than in the short. In this figure, the large-scale factors are referred to as boundary conditions. So why do we use a 30-year period to define the climate? According to the WMO, that's the World Meteorological Organization, this period was first chosen because at the time only 30 years of data was available for many places. The optimal period for temperatures is often substantially shorter than 30 years, but the optimal period for precipitation is often substantially greater than 30 years. So the WMO conclude that the 30-year averaging period represents a compromise for the sake of consistency. The current climate is changed every 10 years. So our current climate is 1991 to 2020, which will change in 2031 to be 2001 to 2030. When we talk about pre-industrial climate, it's usually taken as being the climate as it was before 1850. In some circumstances, we're starting to see people use shorter periods. For example, in the COP process, it's been argued that 30 years is just too long to capture the rapid global warming that we're currently seeing. In between weather forecasts and climate forecasts come seasonal forecasts, the what will the weather be next winter type questions. As the weather is chaotic, this is very hard to do, but there is some skill to be found in looking at the large-scale influences on the weather. For example, if there's a strong El Niño occurring in the South Pacific, then certain weather patterns are more likely to form around the world than others. The North Atlantic Oscillation, or NAO, is another of the many factors which can be looked at. Meteorologists look at the pressure difference between Iceland and the Azores. The pressure is always lower in Iceland than in the Azores because of the large-scale circulation of the atmosphere, which we'll look at in the next film. However, the difference in pressure can vary. A large difference in the pressure, that's positive NAO, leads to stronger westerlies, bringing moist air to Europe. Consequently, the summers are cool and winters are mild and wet in Central and Western Europe. In contrast, if the pressure difference is small, that's a negative NAO, westerlies are suppressed, winters are cold and dry in northern European areas, and the depressions tend to track southwards towards the Mediterranean Sea. This brings increased storm activity and rainfall to southern Europe and North Africa. The Central England Temperature Record is the longest instrumental record of temperature in the world. The data represents the temperature in a roughly triangular area of the United Kingdom enclosed by Lancashire, London and Bristol. The sources of data include records kept by individuals around the country, all carefully combined and corrected for factors such as changing instruments over time, the growth of urban areas and all the rest of it. The precision of the data published for each year represents the number, accuracy, reliability and geographical spread of temperature records that were available for that year. So early in the record, the data may only have a precision of 1 or even half a degree Celsius, whereas more recent data has a precision of 0.1 degrees. The mean monthly temperature record starts in 1659, with daily data being available from 1772 and maximum and minimum daily and monthly data beginning in 1878. The Central England Temperature Record allows us to study both the changing weather and the changing climate of Central England. This image shows both the variability of weather from year to year and the change in climate over time. Both the variability and change are different from country to country. The climate of a particular place for a particular time of year is most fully described as the probability curve, showing the temperatures or rainfall or any other climate variable which are most likely, as well as those extreme temperatures which may occur. As the climate changes, this whole distribution changes. For example, in a warming climate, you would expect fewer extremely cold temperatures and more extremely warm ones. However, extremely cold weather events can still happen, just less frequently. In the next film, we'll look at the atmospheric and oceanic circulation.